When we picture a particle, we usually imagine something quite simple, a tiny, self-contained sphere traveling cleanly through an empty void. This mental model of a distinct microscopic bullet is deeply ingrained. It is how we intuitively talk about the physical world, even in professional physics conversations. But open a modern quantum field theory textbook, and that intuitive picture completely vanishes. The rigorous mathematical reality demands we discard the bullet entirely. If you consult the foundational texts, like those by Nobel laureate Steven Weinberg, you won't find descriptions of tiny physical spheres. Instead, Weinberg traces the definition back to the physicist Eugene Wigner, who stripped the concept down to pure mathematics. Under this strict framework, a particle is defined solely as an irreducible representation of the Poincare group. This means we are no longer talking about an object with a hard surface. We are looking at a mathematical mapping of symmetries. The grid shifts, and the math tracks how a system translates through spacetime. The symmetries rotate and boost, resolving into rigid values for mass and spin. There is no coordinate for where the object actually is, only a catalog of its invariant properties. This creates severe intellectual friction. We are taught to internalize this pure geometric abstraction, yet we still use the same word to describe the physical things hitting our detectors. To bridge this gap, we have to stop treating particles as absolute, classical objects. We have to evaluate them through frameworks that change entirely depending on how closely we look. Confusing the mathematical symmetry for a hard physical reality is where the illusion begins. The core operational question in modern physics is not asking what a particle definitively is. The question is figuring out which framework is most accurate for the specific situation you are probing. This reveals why the traditional debate over whether the universe is made of localized particles or continuous fields misses the mark entirely. It assumes an either-or reality. In practice, physicists rely on effective frameworks. These are specific mathematical descriptions that are highly accurate, but only valid within strict operational boundaries. This scale visualizes our interaction limits, showing how the energy used to probe a target directly dictates its physical nature. At macroscopic or low-energy scales, objects behave distinctly. You see classical scattering, where an entity bounces cleanly off a target. At this specific scale, treating the entity as a localized coin-like object is mathematically rigorous and perfectly matches experimental results. The effective description works. But crank up the energy to probe the extreme quantum regime, and that solid object dissolves into diffuse, overlapping wave-like interference patterns. Here, the point mass is useless. Wave-like features entirely dominate the mathematical description, and the equations must shift to accommodate them. A robust physical framework does not force a choice between the two. It seamlessly accommodates both the point-like and wave-like facets where their effective descriptions are strongest. Forcing a single interpretation across all boundaries breaks the mathematics. If you insist on tracking a hard point-like particle through a high-energy quantum interaction, your calculations will fail. Researchers operating deep in technical minutiae often have to pull back to recognize these broader boundaries, ensuring they are applying the right tool to the right scale. The physical reality of the object is not a fixed absolute state. It is a highly contingent, effective description tied directly to the scale of observation. Yet, even knowing this, there is one classical assumption that remains deeply persistent: the idea of the continuous trajectory. The colloquial definition of a particle demands two things. First, it must possess a definitively measurable location at any given instant. Second, it must trace a continuous line through space and time. On a Minkowski diagram, this trajectory forms a single, unbroken world line moving fluidly into the future. This model relies on a smoothly ascending path, implying a permanent, uninterrupted history. It exists indefinitely. Quantum field theory exposes a mechanical flaw in this logic. The math proves definitively that particles do not last forever. QFT introduces an annihilation operator. This mathematical tool explicitly governs how a particle is instantly erased from existence, terminating its timeline. Conversely, the creation operator spontaneously sparks a completely new particle into reality. It begins moving forward in time with zero prior chronological history. The variability to create and annihilate objects shatters the classical requirement. You cannot claim an entity is defined by an unbroken path when it can vanish and appear in discrete jumps. Any framework attempting to define a particle by a continuous, eternal trajectory is entirely incompatible with a quantum reality defined by fleeting lifespans. If they lack continuous trajectories and are strictly defined by abstract symmetry groups, we are left with a blunt philosophical question. Are particles actually real? The confusion stems from a semantic double duty. We force the single word particle to describe two entirely different concepts. We can see this duality perfectly mapped in this Feynman diagram, uniting math with physical outcome. Looking strictly at the interior geometry, you see the Wigner and Weinberg abstraction, the purely mathematical space where creation and annihilation operators govern interactions. This internal mechanism is completely divorced from anything resembling a physical, tangible object. It is pure calculation. But the framework must eventually connect back to measurable reality. The external legs of the diagram represent the tangible, observable data that actually strikes the collider's detector. In the working language of physics, both the mathematical map on the inside and the physical territory on the outside exist simultaneously, and both are casually called particles. Resolving this tension does not require us to choose a side. We do not have to decide if the universe is exclusively abstract math or exclusively hard matter. This dual ontology, requiring both the abstraction and the observable state, is a core feature of modern physics, designed to handle the sheer complexity of quantum mechanics. Understanding the universe requires stripping away the solid exterior of macroscopic matter and acknowledging the chaotic, temporary network beneath it. True theoretical rigor means knowing exactly which effective scale you are operating in at any given moment and using the vocabulary that matches it. The ultimate lesson of quantum field theory is that the bullet never existed. At the most fundamental level, continuous physical reality is nothing more than a macroscopic illusion.